Hello again. This is Math 2115 coming to you from the College of DuPage. And the title of this lecture is Number Theory, Computer Science Applications, Integer Representations and Algorithms Revisited. As always, please be an active learner as you watch this video. By way of introduction, integers can be expressed using any integer greater than 1 as a base. And we'll show in this section that we commonly use decimals in normal life, but in computers, binary, base 2, octal, base 8, and hexadecimal, base 16 representations are often used. Given a base b and an integer n, we'll show how to construct the base b representation of this integer. We also explain how to quickly convert from binary and octal and between binary and hexadecimal notations. As mentioned previously, we'll have algorithms for doing arithmetic operations using various bases. And we will also introduce an algorithm for finding a divided by d and a mod d functions where a and d are integers with d bigger than 1. And finally, we'll describe an efficient algorithm for modular exponentiation. And this modular exponentiation is particularly important for encryption and decryption, cryptography. So we're preparing ourselves for that discussion. Okay, so in everyday life, we'll talk about 965. This is base 10. That really means that's 9 times 10 squared. This is 6 times 10, and that is 5 times 10 to the 0, which and 10 to the 0 would be 1. So it's this. But it's often convenient to use other bases other than 10, and so we talked about binary, octal, and hexadecimal notation for other things. So here's a theorem that we state without proof. The proof is by induction, and we've covered induction pretty well, and you'll see induction again on the final, but we won't look at this proof today. So what this says is let b be an integer greater than 1. So that's going to be our base. If n is any positive integer, it can be expressed uniquely in the form this way, as the sum of powers of b. So it's n is equal to ak b to the k plus ak minus 1b to the k plus 1 plus dot 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 all the way down to, and this is a1, that's b to the 1, there's an automatic 1 there, plus a0. Where k is a non-negative number, these are all non-negative integers that are less than b, and ak does not equal 0. Because if ak equals 0, you just start with ak minus 1. And that's the that's called the expansion in terms of base b. And the common thing that we do is base 10 in real life, and so that means that that is a decimal expansion. So we can talk about, well, how do we do these other expansions? How do we do a binary expansion? And you can change from decimal to binary, from binary to decimal, from in between all of these things. And those conversions are something that I have asked on the final exam before. So anyway, here's a problem for you to consider. What is the decimal expansion of the integer that has this 1, 0, 1, 0, 1, 1, 1, 1, 1, base 2 as its binary expansion? You know what to do. Let's see how you did. So we just start, what do we go up to? So this is going to be 2 to the 0, 1 to the 1, 2, 3, 4, 5, 6, 7, and 8. So this is going to be 1 times 2 to the 8th, 0 times 2 to the 7th, 1 times 2 to the 6th, 0 times 2 to the 5th, 1 times 2 to the 4th, and 1 times all these other powers of 2, and we add them up and we get 351. Now we're going to talk about the other bases. Base 8 is called octal, and base 16 is called hexadecimal. And by the way, I'm not making separate slides of these, but these are problems that you should consider, something that I could ask you to do, and you may want to pause and try to do them. What is the decimal expansion of the number that has octal expression 70168? Well, this is going to be 0, 1, 2, 3. So this is 7 times 8 to the 3, plus 0 times 8 squared, plus 1 times 8, plus 6. You do all that calculation, you get this number. 16 different digits are required for hexadecimal expansion because you have to have 0 up through 15, and we run out of single digits here, so we create digits, and the standard is that 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. So the question being asked here, what's the decimal expansion of the number with hexadecimal expansion? 2AEOB in base 16. What is that in decimal? And so we go, this is going to be 0, 1, 2, 3, 4, and it's base 16. So this is 2 times 16 to the 4th plus 10 times 16 cubed plus 14 times 16 squared, 0 times 16 plus 11, because B is 11. We do the calculation and we find that this is the answer. Now note that each hexadecimal digit can be represented using 4 bits. For instance, we see that these base 2 correspond to, this is the hexadecimal, so you see this is E, which will be the first block of 4, and this will be 5, which is the second block of that. So this in base 2 is E5 and 16. Bytes, which are bit strings of length 8, can be represented by 2 hexadecimal digits. And these hexadecimal digits actually are used in core dumps. This is a dump of a computer memory where things are being stored. And you can see all these numbers are hexadecimal numbers. So this is something very useful when you want to go into detail about what's really happening in the computer memory. When I was young, people would print these things out and they would be studying pages after pages of output looking like this. Okay, we're now going to discuss an algorithm for constructing the base B expansion of a number n. Now, previously, we were talking about going from a base back to a decimal and some intricacies that exist between base 2 and the hexadecimals and things like that. But now this is a little bit different problem. So first thing we're going to do is divide. So n is our number, and we're going to divide it by the base that we want to change to. We obtain a quotient and remainder. The remainder is the rightmost digit in base B expansion. Next, we divide the quotient again by B, and we get this. And this becomes the second digit to the right in the base B expansion. Continuing this process, successively dividing the quotients by B and obtaining additional base B digits as remainders. This process terminates when we have a quotient equal to 0, and it produces the base B digits from right to left. So I could ask you to find the octal expansion of 1, 2, 3, 4, 5 in base 10. So we divide it by 8 and we get a 1. Successively dividing by 8, we're going to get these numbers. So when we divide 8 into 1543, we get 192. When we divide 8 into 192, we get 24, and we do get these remainders. And 24, we get a remainder of 0 and 3. Now we have the quotient being 0. So the digits that we have found are 1, 7, 0, 0, and 3. Now they go this way, so this is 1, 7, 0, 0, and 3. And so you see that's the order in which they come, and they go from right to left. So that's how we do that calculation. If I ask you to find the hexadecimal expansion of this, we're going to divide by 16. So we divide by 16, we get this, remainder of 10. Next time we divide by 16, we get 691, remainder of 14. Divide by 16 again, and we get 43, a remainder of 3. We get 2, remainder 11, and then we get 0. That means we're really finished with 2. Now we write these from right to left, so we start with 10, 14, 3, 11, 2. So it's going to be A, E, 3, B, and 2. And that is the expansion. Now we can find the binary expansion of this by dividing by 2. Dividing by 2 again, 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 again. We're taking just the remainders. And you see we go from right to left. So this is 1, 0, 0, 0, and 4 ones. Now, we can write algorithms for this. I mean, we just write in pseudocode what we do, and if you're programming in a given language, you could write something that would do this calculation for you. And this is the kind of algorithm that you would write. So you go through and notice that we're using the functions that we talked about in the previous lecture in order to do that. And here's an example of how some of these representations of integers from 1 through 15, this is decimal, hexadecimal, octal, and binary, how they look. We can also do calculations with these. Let me talk about how we do calculations, and I do expect you to be able to do these calculations too. This is base 2, so we're taking this number added to this number. So we start over here, and we take 0 and 1 is 1. Here 1 and 1 is 2, but 2 in binary is 1, 0. So we put down the 0, we carry our 1. This is 1 and 1, and 0 is 2. But how do we write 2 in binary? We put the 0 down, and we carry the 1 again. Here I get 1 plus 1 plus 1. That is 3. How do we write 3 in binary? We write 1, 1. So we put down this 1, and we carry the 1 that is in the 2 to the first power, and we pull that down. And so that means that this sum is 1, 1, 0, 0, 1. And then you can write an algorithm for that. And the algorithm that we just talked through here is big O of n, where n is the it's an n-bit integers, adding 2 n-bit integers. So here we were adding 2 to the 4th, so that took us like 16. Let's see, this is 2, this is 4, n is 4, so it's big O of 4 is what this takes, because I have to do 4 calculations plus the carries. Okay, and you don't always do the carries. Let's do another one then. Let's look at multiplying this number times this number. And again, we do the shift just as we do in base 10. So when we take 1 times all of these things, I'm just going to get 1, 0, 0. But then I have 0, so these are all zeros. Then I'm taking 1 times 0, 1 times 1, and I get this again, but I add them down. But now I'm adding them using base 2. So that is 0, that is 1. This is 1, but we do be mindful about carrying. This is 1 and this is 1. So that's how I would multiply. Now there are more efficient algorithms than the one we just used for multiplying, although this is simpler if you're doing it by hand. And there's one algorithm which, instead of being big O of n squared, as this one is, it uses big O of, and this is 1.585 bits. Now you might say that's not a big difference, but in a big problem for n that could make a difference. And this is something that theoretical computer sciences people do a lot. This is the kind of research that they do. And you can have algorithms for finding the a divided by d, or what is the remainder, both the divisor, the dividend, and the remainder. And so we can have algorithms for that. Here's an example of the algorithm for that. And we discussed this calculation in the previous lecture. Now there are even more efficient algorithms than this one for determining the quotient and the remainder. This is actually one of Knuth's papers, and he, of course, is the guy for computer science. And so these algorithms require, this is the best you can do, it is log of A times log of D, big O of log of A times log of D, bit operations. If both are binary, contain fewer limits, we can replace this by n squared. So that we need to have big O of n squared if we're doing that kind of calculation. Again, these are things that theoretical computer science spend a lot of time doing, and when they incorporate this into compilers, it saves a lot of time. In encryption and decryption, or cryptography, it's important to be able to find b raised to the n mod m efficiently. This is modular exponentiation, where b, n, and m are large integers. Now, it's impractical to first compute b to the n and then find its remainder. The problem just gets too big when these are large, because b to the n will be an enormous number. Instead, we can use an algorithm that employs the binary expansion of the exponent n, and this is actually really quite clever. Now, before we show you the algorithm, we're going to illustrate the basic idea. So we will first explain how to use the binary expansion of n to compute b to the n. And this is related, except we're not changing it to mod m. But note that then that b to the n is an integer, and so it can be represented as b raised to the, here's a number, it's either 0, 1 times 2 to the k minus 1 plus ... all the way down to this. So basically you're representing the exponent, and let's say the exponent is this, that's what I'm doing, in base 2. So b to the n is b to the this power. But then that is the product of these numbers, because when you add exponents we do that, so it's a product of these numbers. So this shows that to compute b to the n we need to only compute the values of b squared, b squared, and so on and so forth in the correct order. So once we have these values, we multiply the terms on the list whenever it's 1. Whenever it is 0, you don't need it. And so for efficiency, after multiplying by each term, we can change this into mod m. In fact, that's what we're going to do in our algorithm. And so here's an example. Suppose you wanted to compute 3 to the 11th. Well, you first break 11 into its binary representation, which is this. And then you note that 3 to the 11th is, I add these exponents and I get that. So by successively squaring, you find that 3 squared is 9, 3 to the 4th is 9 squared is 81, and 3 to the 8th is 81 squared. So I multiply those three numbers together and I get this number, which I can change into mod m for whatever m I'm looking at. Okay, so what does the algorithm then we're doing? Well, it successively finds b mod m, b squared mod m, b to the 4th mod m, all the way up to b to the 2k minus 1 mod m. And again, realize that we figured out what those coefficients were for the binary expansion of n. So then what we do is we multiply together those terms, b sub 2 to the j, for j equal, go from 0 all the way up to 2k. And then each time we find the remainder of the product when divided by m after multiplication. And so we go through this. Now this is a pretty efficient algorithm, But to compute the values of the mod function, you don't necessarily use algorithm 4. There might be a better one. So anyway, here is this algorithm that we have to do modular exponentiation. And as you can see, it is a recursive thing. Let's look at using this algorithm to find 3 raised to the 644 mod 645. Now you do have to write code to do this, or there are code in the compilers that do this, but this is often a question on qualifying exams dealing with discrete math, and so you do need to know how to do this. I know that there are questions like this on the University of Chicago entrance exam to graduate discrete math programs or graduate computer science programs. So anyway, let's talk about how to do this. Now note that I take 644, and that is base 10, but I change it into binary. Now you should check to make sure you get this, but that is what you get for the binary expansion. So we got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means that a sub I is 1, and that is and that starts at 9. Then I got 8, 7, and so on and so forth. So I'm looking at these digits, and the only ones that are going to be included are the ones in the product, are the ones where there's a 1. So there's a 1 here, a 1 here, and the last one is down here. So you see it becomes a simpler calculation. Okay, now the algorithm starts initially with x equal 1, and the power is equal to 3 mod 645. Now that 3 is the base, if you look back at the algorithm. So that's 3, and 3 mod, this is 3. So that's where we start. And then we start computing 3 to the 2j, for j equaling 1, 2, 3, all the way up to 9. And the reason we did that is because that's the binary expansion. By successively squaring, and each time we check and we reduce it modulo 645 if the number's getting big. If aj equals 1, the places where it's 1 in the expansion, it's multiplied by the current value of x by 3 to the 2, 3 raised to the 2, and that's raised to 2j. So j is an exponent on the 2. Mod 645, and we reduce the result to mod 645. So here are the steps used. So you build it out this way. For I equals 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And at the result, we have this one times this one, which is a big number, but we reduce that to mod 645 using the functions that we have, and we find that this is 36. This might look onerous, but it's really much quicker than other ways of doing it. And 3 raised to that number is an enormous number. And actually, algorithm 5 is quite efficient. It is big O of log of m squared times log n bit operations to find b to the n mod m. Okay, so these are calculations that you want to be able to do and understand. And these will come up again in encryption. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.